Okay. Can you hear me? Okay, perfect. So yeah, I would actually like to stay and talk with Elias about all the stuff he mentioned because like my presentation will be very similar or at least touching the same topic. But okay, so first question like who is cryptographer here or like mathematician by design? Okay, so I can lie to you and no one will tell. Okay, so basically, like I will be touching the very similar topic which Elias was talking about, and this is basically like scaling zk-Rollups with hardware. Like, what's possible? Basically, he was mentioning like zk costs like 45K to 1 billion on infra cost, but this is like this huge range, right? Like, how the f you went from 45K to 1 billion, right? It's like, oh, oopsie doopsie, like my accountant made a mistake. So basically, that's what I want to talk about. So, I will not talk about the ZK. I guess you are all expert after the previous talk, but we know ZK is good. Z- okay, ZK is good. It's maybe fast and it's secure. That's good. And we have like kind of like two ZK in this room. One is for privacy, the second one is for scaling. So I will not be talking about someone referring to ZK. I will be talking about the snarks, the succinctness part. So no, like not for privacy purposes. And why I will be talking about this. And actually, I chose like Hello 2 with KZG, which Elias was talking. This it's shit. I don't think so. I mean, it's in production. The chains are doing good. We have like several teams working on this. They did tremendous work, and okay, so we are back. And basically, I would say you can use, like Hello 2 for something else than zk-Rollups. Like, we don't, all of us have to have our own zk-Rollups. You can build, like, some other cool stuff like zk email, which was also is written in zk, in Hello 2 with KZG. So let's say, like, Hello 2 is good. And, okay. So the problem is, like, zk is the great computation. It's succinct. So we can verify, like, the, statement very succinctly. But we are paying, right? Like, there is a catch. So we are paying for the proof generation. And how much? Like, I don't know. Or like, I know, I will tell you later. But basically, why, right? We have like this all fancy word like commitment, hashing. You heard maybe like MSM several times last year, FFTs. Basically, that's like where we are paying the price for succinct verification, right? It's like asymmetric game. Kind of, you can verify a lot, but you need to pay price somewhere. And the price is proof generation. Okay, so if you will, just having some Friday nights out and you will be bored, you start profiling like Hello 2, right? Because what else would you do? Like basically that's like pretty common. And you would get this picture, right? So this is like the Hello 2 KZG with 128 transaction to the 20 and to the 20 of the size of the circuit, right? So it's like pretty common ZK-L2. And you would find out like we have like these bad actors, like not really bad, but like the guys who are like responsible that the zk is slow, and there's like multiscalar multiplication, entity or like FFTs, and custom gate evaluation. So I mean, if it would be like 2022, I would be talking about MSM and how we did like tremendous work, how we speed up FFTs. But like this problem, this is solved. Basically, like the Z price. Maybe you heard someone about the Z price. Yeah, someone. Okay, they solved this basically. I mean, it's not that it's solved, but it's like we did pretty good job. It doesn't make sense any like not that it doesn't make sense. We don't have to spend too much time on it. But if you will zoom in, right, you will see like these MSM entity and custom gate. They take quite significant time. So like you can see like the button. Okay, you cannot hear me. So you can see it takes a significant time in the whole computation. So it's actually like 80%. So if we will tackle like those fours, we will solve kind of like 80% of the computation. So I don't want to go into the details of Amdahl's law, but if you will speed this, you get some speed up. Basically what I want to say is like let's focus on this 80% and we will be good. Okay, and you can see actually the MSM is not 80% of the computation, which maybe you were told before. Okay, so like CPU baseline, right? okay, I still have time. So if you will run your rollup, in AWS or on bare metal, and you will use CPU because, like you spend all your money on marketing and you don't have any GPUs left, basically that's how much it will cost. How much it will take to generate one proof. And this one proof is basically, as I said, 128 transaction of the secret size to the 20. Okay, is this clear? You will see this table several times.
Like 128 transaction, like on linear scroll or anyone?
Yes,
But why by circuit size? Why is by times?
by. What's not clear?
You said
This is like, I'm not sure if it's ERC transaction to be honest now, or it's like, just if, or like, yeah. I'm not sure if it's ERC actually, so that's, I actually was asking that myself.
And what is the circuit size? It's just the zk-EVM as a whole?
Yeah, this is like super secret.
Okay.
Yeah, it's, but it's one secret. Let's leave it with that. It's more complicated, but it's like, the secret size is like 2 to 20. That's what is important. Okay, so yeah, I just took, like one machine from AWS and one our machine, so like machine of our partner. And yeah, basically it will take like 30 minutes on like bare metal, let's say, but you can see like the processor is like 2 times slower in terms of the cores, or like almost 2 times. And it will take like 27 minutes in AWS, so you would get proof every 27 minutes. Like, I mean, that's not great, but better than 7 days. But of course, you can have several proofs, right, running in parallel. But okay, so 30 minutes, that's how much does it take to generate one proof. So yeah, there is some potential for improvements, right? So either you can be like cryptographers, which seems to be none of us here are cryptographers, so we are screwed. So what we will do, like basically we will spend our monies, right? So we will acquire some GPUs, not FPGAs, please don't spend your money on FPGAs. If you are not Binia's team, don't do it. And ASICs, well, we don't have any ASICs yet. Several teams working on this. I'm looking forward for them to deliver because I believe there's a huge potential, but unfortunately, we don't have ASICs today. So yeah, let's go with the GPUs. What actually GPUs can do for you? Like, I mean, what really GPUs can do for you? So if you will like, I don't want to spend too much time because this I think is like 2 years old topic, but if you will accelerate those MSM FFTs, that's what you can get, right? You will get to the 22 minutes or 24 minutes. So just, for comparison, like you basically, you wrote Omer from Ingoniana, you saying, hey, my prover is slow, can you do something? He will say, yeah, pay me license for Icicle, I will save you like, 7 minutes. And you are like 7 minutes faster by like writing to, one guy, Omer, somewhere on Twitter. So yeah, there's like, 10% speed up to 25% speed up. But what's important, like you already have like 80 GPUs. So look at the table. I'm not using one GPU, I'm using like 80 GPUs. So there is like small trick. You're already paying a lot. So maybe take a moment just to see this graph. So you're paying some significant amount of money. You saved 7 minutes, but you are utilizing GPU only to like 2%. Not great, right? So, I mean, this is like 2022, let's move on. We accelerated MSM, we accelerated FFTs, let's do something more. So, there is like, I was talking about this third, like, computation, which is called custom gate evaluation. So, unfortunately, none of us here are cryptographers, so I will just say like, it's important computation, you need to have it in place. We can talk details later, but basically we will exploit the structure. So basically you can see there is like indices on the left side, right? 0, 1, 2, up to 1 million. And actually, when you usually see such a thing, you start thinking, okay, can like maybe one thread compute over the whole table? Or does this thread needs to compute something else? And we just find out actually one thread can compute over the whole table. So actually, can you hear me? You can do like split the whole computation over the table to one thread like this. So you don't have to wait like for one thread to compute over the whole table, but you will you will basically leverage like, single instruction multiple data, which is great because we have, this Chinese guy, CEO of NVIDIA happens to be, and he gave us like GPUs, which are really great at this. So what's like this computation look like? So on the CPU, we actually have 8 of this computation. Why? Because we're going to the extended domain, which is like 8 times. Why? Because like we're computing some quotient polynomial, but like those are like mathematical details. That's like which needs to happen, right? We know it's like we multiply this computation 8 times, and one computation, this box, takes on CPU like 48 seconds, right? But we need to do it 8 times. That's the important. So the whole computation takes almost like 400 seconds, okay? And even though like Hello 2 already has some heavy parallelism in place, but this parallelism happening within the inner loop, right? So you can see we're actually parallelizing the inner 4. So actually this is like parallelized, right? But these 8... But those 8 computations, they are not parallelized, right? So I mean, we are smart here, right? We bought GPUs, so let's use them. Yeah, but then basically we will find out like the GPUs, they don't have infinite memory, right? Which is like, suck. And basically like, the circuit is pretty huge. And also you need, it's not like you computing only over the one piece of data. You're actually computing over like 200 indices. So you need all this data on the GPU. So then it's like, shit. So basically like, you need like 67 gigabytes of memory. Well, I have this beautiful GPU here, which I can sell you, but it has only like 24 gigabytes of memory. So yeah, we need to do something. And basically like, again, I will not go into the details, but you can come with some chunk processing and optimize like, how do you reduce. So actually you don't need all the data in one place, but you can actually chunk the circuit and you need only some intermediate values. So exactly what is happening, like one thread is computing, that's like the orange color, and then we actually like just chunk process this over this table. So that's like the rotations, like the red colors. So I know maybe this is like a bit misleading if you don't know what's going on, but basically we solved the issue. That's like, we are great, right? We are like celebrating because we went from like 30 gigs of memory to 4 gigs of memory. So now the whole computation fits to one GPU. Okay, so what's the baseline, right? So we have like single GPU, and if we will run this computation, we actually save like what? 29 seconds. That's good or bad? What do you think? It's not great, right? You're paying a lot and you just save like 29 seconds, right? It's okay. It's not great, it's okay. So basically, but still holds, we need like 8 of this computation, right? So it's like 19 seconds times 8 is still like 152 seconds. So we went from almost like 400 seconds to 152 seconds. Not great, but like, that's not what, wanna, this is not the asymmetric return, right? You wanna pay a lot, but you wanna speed up a lot. So actually, you can use different GPU, right? So what can GPU do for you? If you will switch from L4, which is like 19 seconds, to 4090, you almost saved 50%, right? So you can see like you can go like from the 90 seconds to 10 seconds. So this is maybe interesting, right? And the 4090s are not that expensive compared to L4. But yeah, you saw, maybe remember, I had the 8 GPUs actually on the server. So this is not some black magic, right? This is like kind of obvious. You can split this computation amongst the 8 GPUs and compute it at once, in parallel, right? So actually, we will really go from these 400 seconds to 19 seconds. And that's actually, you're paying a lot, but you are already starting to getting something on return, right? Okay. So now we kind of saved, like, we went from 400 seconds to 19 seconds, and then you are checking, and then you see, you will start your computer, inside system, inside compute, and you will find out actually, you spend like 6 seconds on data transfers. This is like, okay, we are back. I don't want to say like bad, but it's like, you actually realize like the compute is not the problem is memory. So either like the memory is restricted because you don't have enough memory, or actually you need to like transfer data, right? The compute is great actually. The compute is not a problem. So if you know like heard someone like about the acceleration, just think about it like usually the memory is the problem, not the compute. But okay. So can we do something? Yeah. I mean, this is, if you ever heard about the GPUs, you wrote some code, you basically can leverage like multiple streams. So actually you can see the first case is like really, I don't want to say stupid, I would say naive or like simple. And actually it's like, you copy some data because we're doing these chunks because of the memory, so we cannot process the whole circuit at once. We need just chunk of the data, then we execute the kernel, and we're doing this and that, right? So not great, but actually you can mask the execution with copying the data, right? That's like smart, and actually you can save like we went from 19 seconds to almost 14 seconds on the L4. So, so yeah, that's pretty nice, right? And okay, so what does it look like at the end? So what GPU can do for you, right? That's like where I will answer the question. It's basically if you can like with 80 GPUs go from like almost 400 seconds to 14 seconds. There's like 27 times improvement, and this is getting to somewhat interesting. Or if you will use like 3090, 4090, you can get almost like 40 times speed up, right? And this is what you want to get. If you are paying a lot, you want to get at least this. Okay, yeah, so this is like just the wrap up. Like, so we basically went like from 30 minutes or like 27 minutes on the CPU to 17 minutes on the GPU, right? And then like Elias was mentioning, basically how much does it cost? So basically one of these machines in cloud, which is like AWS, the GCP will be very similar, costs like $9,000, right? This is in Frankfurt, so pretty expensive region. I know you can get some cheaper, but I would say it's a lot. Basically with us, we're building servers. Our partners, Rockaway Infra, is building server, and we have like faster server and 3 times cheaper. So I would say like zk is already on a good track or like way to become cheaper because this is the most expensive it ever been, from this point of time. Okay, and thank you all.